Okay, welcome everyone. We're going to have a lot of thinking about what is intelligence, what is learning, and what is possible in the years ahead. I've known Yann as a wonderful colleague since 1990, the old days at Bell Labs Research. Back then, he was showing us it's important to do fact propagation. Since then, he's done so many wonderful things. And more recently, he and the godfathers of AI, or godfathers of deep learning, have given us the idea that deep learning is a powerful idea, which has really struck a chord worldwide. So that's about it. He's done it all, and he hasn't stopped yet. So I'm curious what he's going to do next. So let me now turn it over to you, Yann. Dr. Yann LeCun.
Thank you, Doug. Well, thank you for the invitation first. A real pleasure to be here. I hope you can soon see my slides. Okay, a path towards autonomous AI. This is the title of my slide, and I'm somehow not seeing my first slide, but that's my fault. What I'm going to talk about today is a little bit about the state of the art, but mostly about what I think or where I think AI research should go over the next decade, perhaps, or at least the next few years. With the idea that we want to push AI system towards something akin to human level intelligence, but I've been saying for quite a while that before we get to human level intelligence, we're going to have to get through things like cat level intelligence and maybe dog level intelligence and things like that, because current systems that we can build today don't have the type of common sense that we observe in animals. And even the systems currently that we think are really the smartest don't have much common sense and have a very superficial understanding of how the world works. So let's dive right in. A lot of applications of machine learning today and AI are basically based on supervised learning, right? And we know the principle of this. You want to train a machine to classify images of cars and airplanes. You show it lots of examples of cars and airplanes, and if you show the image of a car and the system doesn't say car, you kind of tell it this is a car, and you adjust the internal parameters so that the output gets closer to the one you want. And then, if it produces the right answer, you do nothing. So that's supervised learning. That requires a lot of training samples. There's another type of learning called reinforcement learning, which I'm sure many of you have heard of. And there you don't tell the system what the correct answer is. You merely tell it whether the answer you produced was good or bad. And there's an added complexity here, which is that you don't tell it very often. It could be that the system plays chess, and then at the end of a game, it gets to figure out whether it won or lost, and then it has to adjust its parameters. So that's called sparse reward. And the problem with RL is that it requires an enormous amount of interactions for the system to learn anything. Many, many more interactions than what humans seem to need to be able to learn a new task. So those two paradigms of learning are really not that efficient. And in fact, it's a big practical issue, because we'd like to be able to get machines to learn how to drive a car, for example. And whereas any teenager can learn to drive a car in about 20 hours of practice, we still don't have completely autonomous level 5 self-driving cars using combinations of supervised learning, reinforcement learning, and even self-supervised learning. So self-supervised learning is something I'm going to tell you about a lot. And I came up with this picture about 7 years ago, and which I showed, and it became a bit of a meme in the machine learning community. And this was a way to explain that the amount of feedback you give a machine when you are using reinforcement learning or supervised learning is very, very low in terms of information content. And so we need to come up with new paradigms like self-supervised learning, where the feedback that the machine gets at every training step is much richer, and so the system can learn more about the world when every time it sees an example. Yeah, I first showed this slide in this picture, this analogy in January 2016, so it's a bit old. So self-supervised learning, back in 2016, this was something I was kind of advocating for, but really hadn't kind of come to the fore, really. It was clear it was going to become important. And in the meantime, self-supervised learning has completely taken over the world, at least the world of natural language processing, maybe speech recognition, translation, things like that. Not so much computer vision yet, and I'll come to this. But self-supervised learning really has become one of the techniques that has brought about all the progress that we see in AI today. So what is it? A very simple way to explain this is self-supervised learning can capture the internal dependency within an input, for example, through prediction. So let's imagine that you see a segment of a video and you pretend that you don't see the remaining of that video. You train a system to predict the continuation of the video. And then you reveal the continuation of that video, and the system adapts itself to make that prediction. So it's not just predicting in time, it could be predicting in space, it could be predicting backward in time. It doesn't matter. Essentially, you have a partial or obscured or masked view of an input, and you're trying to essentially capture predict what remains that you can't currently observe in the input to some extent. So here's an example of that, a particular example, which is called a denoising autoencoder, and an instance of this is called a masked autoencoder, and this is the main technique that is used to pre-train natural language understanding systems. So you take a piece of text shown here at the bottom, let's call this Y, you corrupt it in some way, and the way you corrupt it is by basically blanking out, replacing some of the words by a blank marker, or by substituting some of the words. So you get a corrupted version of that sentence. You run that through some big neural net, and that neural net is trained to predict the missing words. So it's basically trained to reconstruct the perfect sentence, if you want. In the process of doing so, that system has to learn an internal representation of the sentence that captures the grammar, the semantics, a lot of things. And so this was kind of inaugurated by this paper from Google, by Devin, a system called BERT. And there's been a lot of variations of this. One from my colleagues at FAIR, it's called Roberta, and it's open source and everything. And you can use this to pre-train an NLP system, and it works amazingly well in the sense that you can then use the internal representation produced by the system and feed it as input to a subsequent task. So another neural net that you fine-tune for a particular task, let's say for translation. Okay, so all of this nowadays, those neural net architectures are based on an idea which essentially is a kind of differentiable memory, if you want, or associative memory. So there's a module in all of those systems nowadays called transformers. And the basic module of a transformer, in a particular instance, is one in which you feed a vector to a system, and you compute the similarity between this vector and a bunch of key vectors using a dot product or a cosine distance of some kind. Then you take the numbers coming out of those dot products, you feed them to a softmax, which takes exponentials and normalize. So you get a number of coefficients here between 0 and 1 that sum to 1. And then the output of the memory is the weighted sum of a bunch of value vectors weighted by those coefficients. Okay, so you can think of this as an associative memory, and it's all differentiable. You can backpropagate through it. You can update the value and the key vectors using gradient descent. So that's a very useful module. And the idea for this goes back to a paper by some of my colleagues at FAIR in 2014, and others almost simultaneously at DeepMind and later. And if you use this module and you use it in such a way that the keys are other inputs, you get what's called a self-attention circuit. So basically, you have a bunch of vectors coming in. The vectors may represent words, for example, or more generally what we call tokens. And then you compute the matrix of similarities between each of those tokens by computing the matrix of all the dot products between the two, between all the vectors. You normalize the columns of that vector, and then you use those as coefficients for an associative memory that retrieves some value. And you turn this into a module inside of a neural net. So this is called, you also multiply the number of such associative memory heads. And so you get this basic module here where you have this multi-head attention module. You normalize the outputs, and then you have a layer of a neural net. You normalize again, and that's basically what's called a transformer module. You stack n layers of those, and that gives you a transformer. There's another piece here which is designed to kind of produce output tokens also autoregressively, which I'm not going to go into. So this type of architecture has been incredibly powerful. The reason being that those are really useful. Those transformers are really useful when the input tokens are meant to represent objects. And what matters is the relationship between those objects. The reason being that the function computed by a transformer is equivariant to permutation. So if you permute the input tokens and you run through the transformer, the output will be permuted the same way, but otherwise unchanged. So that's a very interesting property, because it means that it doesn't matter in which order you show the things on the input. The system will figure out, like, which combination of input matters for computing the output, and will produce essentially the same output up to a permutation. So this is similar to the kind of property that we have in convolutional nets, where in convolutional nets, when you shift the input, the output is shifted, but otherwise unchanged. The combination actually of convolutional net and transformer is very powerful in a lot of situations. So you can use this for a lot of different applications, including things like getting systems to understand language in multiple languages. So you can use a transformer, pre-train using this masking idea, and then use the internal representation of those systems, train with sentences and text from multiple languages to essentially translate any language into any other language. You can even train those systems to do symbolic mathematics. So this is, again, some work by Guillaume Lample and François Charton at FAIR in Paris. And what they did was generate a bunch of pairs of formulas encoded as text. And those formulas represent a function. And then they train a system to essentially compute its integral, okay? And you can generate a lot of data, because you can generate a random function, compute its derivative symbolically, and then train a system to basically reverse the process. They've done similar things with differential equations and things like this. And those systems are doing a really good job at actually computing symbolic mathematics, integrals, solving differential equations symbolically and things like this. And they're basically treated as a translation problem fed to those transformers. So pretty amazing results. You can use them for dialogue systems. And we've seen sort of, public, ChatGPT is kind of an example of this. This is an older system that combines from FAIR called Multimedia Blunderbot, which combines one of those dialogue systems from text together with a sort of image understanding capability. So training those, we can make those networks enormous, several hundred billion parameters, and because they have essentially what comes down to hardwired associative memories inside of them, they can store an enormous amount of data and sort of interpolate and generalize to some extent. And those systems, once pre-trained, are really giving excellent results on things like hate speech detection or a number of natural language processing tests, including text prediction, right? So you give them a prompt and they will continue that prompt, and everybody has become familiar with this now with things like ChatGPT or GPT-3. Here's another application for language translation that was put together again by some colleagues at FAIR. This is a project called No Language Left Behind. And this system can translate 200 languages in any direction, all the 40,000. But what's interesting is that because of self-supervised learning, this system is only trained on 2,400 language directions. So we only have data for 2,400 pairs of languages. They cover all 200 languages, but not all 40,000 directions. And despite that, the system actually does a good job translating from any language to any language. Most pairs actually in these 2,400s have less than 1 million sentences to be trained on. Those are the 200 languages that it can translate, and a lot of them are what's called low-resource languages, for which there is a relatively small amount of text and very small amounts of parallel text with any other language. More recently, another team has been able to translate languages that actually are not written. So this is a direct speech-to-speech translation system that does not require to go through written text, which is kind of amazing. Another example of self-supervised learning application here is for speech recognition. This is a system called Wave2Vec, also built by some of my colleagues at FAIR. And with 10 minutes of label data, they can reach the performance that would have previously taken about 100 hours of label training data. I'm going to speak a little bit about the kind of techniques that are used for this next. So deep learning and self-supervised learning in particular nowadays are used for a lot of applications. Probably the biggest deployed applications are used in online services like Google, YouTube, Facebook, Instagram, Amazon. Those companies nowadays are really built around deep learning. If you take deep learning out of them, they literally crumble. And what those methods are useful for is basically dealing with the information deluge and ranking things like search results, answers to questions and things like this. And that requires machines to understand content, of course. Translation, of course, is a big application, and speech understanding, speech recognition, and speech synthesis, of course, because about 800 million people in the world are illiterate, 300 million are visually impaired, and 3 billion people can't use technology today because they just don't have access to it or the required skills. So AI is going to help bridge that gap, and that's a big positive application of AI. A big application of AI developed in online services, particularly things like Facebook, particularly those systems I was just mentioning, transformers pre-trained with self-supervised learning, is for things like hate speech detection and content filtering more generally, or what we call integrity. There's been an enormous amount of progress in the accuracy of those systems in the last 4 or 5 years due to this progress. And so those large NLP systems have been deployed for several years by Meta and Google and others. This is not a new phenomenon, even though the public just realizes that the extent to which those things work well recently. But those things have been really deployed on a very, very large scale for years now. For example, hate speech detection on Facebook can be done preemptively by AI system before anybody sees a piece of content about 95% of the time nowadays. And that number was closer to like 30% about 4 years ago. So again, progress in AI has direct impact on services that people use every day, but they don't realize it because it's behind the curtain a little bit. Of course, a huge amount of progress recently in generative AI systems, and a lot of them are based on what's called autoregressive generative architectures. So it's very similar. The way you train those systems is very similar to what I talked about before. You take a piece of text and you mask part of that text, and you train the system to predict the parts that are being masked, that are not available. But in the case of large language models or autoregressive generative architectures, the only thing you mask is the last token. Okay, so I take a piece of text, turn it into a sequence of tokens, basically words, and take the last one out, and train a system to predict that last word by showing it to it. So it's self-supervised because you're using a supervised learning algorithm to basically predict the next word, but it's self-supervised in the sense that you don't need anyone to manually label the output. It's part of the input. Okay, so take a sequence of tokens, run it through an encoder, let's say a big transformer, run this to a small network that's is going to produce the next token, or at least a probability distribution over the next token. And then the autoregressive prediction is that now you take that predicted token, shift it in the context. Now the context is shifted by 1 to the left, and predict the next token. Okay, this is how ChatGPT works today, and many others. Okay, so I put one token after another. Those things can be trained with, can have billions of parameters, anywhere between 1 billion and 500 billion. They're trained with enormous amounts of data, something like a couple trillion tokens extracted from text corpora on the internet. And then you can fine-tune them for various applications, dialogue, question answering, etc. There's been a number of those systems that have been built in various companies, but the only one that has made it widely available to the public is ChatGPT, which is why everybody is talking about it. The other one have been sort of kept behind the walls. And the reason for this is that those systems are not really reliable. They produce text, but the text is not factually correct. And so companies like Google and Meta have a lot to lose by putting out a system of this type that will spew nonsense. It's much easier for a small company like OpenAI to do this. The performance is kind of amazing, really, but those systems make stupid mistakes, and they make factual errors, logical errors. Their outputs are inconsistent. They are very influential. Depending on the prompt that you type, they may agree with you that 2 + 2 = 5. They have limited reasoning ability, no way to really control the toxicity of what they produce. And what's more important is that they have no knowledge of the underlying reality of the world. They're purely trained on text, and so their understanding of the world is really superficial. They have no common sense, really, or very superficial forms of common sense. And they can't really plan an answer because they produce those tokens one after the other. Excuse me. But you can use those techniques also to generate images. So this is a system called Make a Scene that was produced again by my colleague at FAIR last year, where they use one of those autoregressive transformers to produce image tokens from which an image can be generated and sort of made nice. So that system can generate images from a textual description as well as a sketch, perhaps, of the type that you see here at the bottom. And every time you ask it to generate an image, it will produce a different one. And so those are, there's been comparable systems produced by OpenAI and Google and various others using either autoregressive synthesis or diffusion model, which is kind of a different technique for the same thing. And those are really impressive. I mean, they're probably going to have a big impact on content production because it gives a lot of sort of creative ability to people who don't necessarily have the technique for producing things. So this is a different system. So this one is available to play with. Make a Video.studio. This was again produced by my colleagues at FAIR, and it's using a diffusion model to produce short videos from a textual description, including things like swimming fish and dancing robots and sailboats and whatever. Okay, but the long-term vision of AI is that we'd like to have virtual assistants that essentially have human-level intelligence. And there are practical applications of this, believe it or not, in particular because maybe a decade or two from now, we will not be carrying smartphones in our pocket. We'll probably be wearing augmented reality glasses or things that can dialogue with us at all times, perhaps have vision capability and superimpose information on top of the real world, as we walk down the street. And so basically merge the real world and the metaverse, if you want. And to be able to have assistants of this type, we need machines that essentially have common sense, that have human level intelligence. And so this is the question: how do we build those things? How do we get machines to move towards what I call autonomous AI, which really is sort of another word for human level AI? And we need machines that are capable of reasoning and planning and have some common sense. So we have to realize that machine learning sucks today. Pardon my French, at least compared to humans and animals. As I said, supervised and reinforcement learning require insane amounts of samples, whereas humans and animals seem to be able to learn very quickly from a small number of interactions or examples, and they do have common sense that is accumulated. And the question is how. Now, the systems I talked about, most deep learning systems today, including things like large language models, have a constant number of computational steps between their input and their output. And that really is not a good way of doing reasoning. Reasoning can take a very long time, unbounded amount of time. And so how do we get machines to reason? Those systems, because they are reactive and produce one token after the other, cannot plan. They are reactive, okay? And so humans and animals understand how the world works. They can predict the consequences of their actions. They can perform chains of reasoning with essentially unlimited number of steps. They can plan complex tasks by decomposing them into sequences of subtasks. How do we get machines to do that? And the first question, of course, is how do humans and animals learn so quickly? With self-supervised learning, perhaps, but here is a chart that shows at what age babies learn basic notions about the world. Things like intuitive physics, the fact that every object has inertia and will fall under gravity. This is learned by babies around the age of 9 months. So it takes quite a while for babies to observe the world in ways that allow them to understand intuitive physics, essentially. And it's a continuous process, starting from day one, essentially, actually, probably before being born. So how can babies learn how the world works? How can teenagers learn to drive in about 20 hours of practice, whereas we still don't have self-driving cars? How is it that perhaps common sense results from the accumulation of all of this background knowledge that is learned? Okay, so I think that takes us to the three main challenges for AI and machine learning over the next decade or so. One is learning representations and predictive models of the world. I'll talk in more detail about what I mean by predictive models, and that's going to use self-supervised learning to reason, and learning to plan complex action sequences. I must say that number three is not something that anyone can do today. So I'll start by giving a framework. I call that a cognitive architecture capable of reasoning and planning. And there is a position paper that I put online the beginning of last summer at this address, Open Review. It's a discussion forum, so you can make comments and ask questions there. I gave a technical talk a few months ago at Berkeley, which is on YouTube, which is sort of another version of the talk you're about to hear now. So here is the cognitive architecture. It's a modular system that is basically built around this a world model, and the world model is meant to represent all the knowledge about how the world works that the system has learned from mostly observation, a little bit from interaction. And the world model basically is there to predict what the world is going to look like, starting from the observed state of the world given by the perception system, and given the set of actions that we can imagine. So if we can imagine how the world is going to change as a result of our actions, then we can plan a sequence of action to arrive at a particular goal. Whether the goal is satisfied will be measured by a cost function. So this is a module inside the system that measures to what extent the predicted state of the world will satisfy a goal or task that we set the agent to fulfill. And what the system is going to do is basically figure out a sequence of actions that, when fed to the world model, is going to predict that the task is going to be fulfilled given the current state of the world estimated from the perception. You can ignore the other modules for now. I'll come back to them. Now, this idea of having a cognitive architecture goes back a long time in the history of AI. And I thank Pat Langley for pointing me to this paper of his that is a review of a lot of this work over the years. So many systems, I'm going to say a lot of those systems, integrate perception, action, planning, etc. Planning being a really important component of AI classically. Few of them have learning abilities to the extent that I'm hoping this architecture eventually will have. So for most of those architectures, learning is, the emphasis is on planning and solving problems and memory and kind of storing memories and things like that, rather than learning in the sense of neural net learning, if you want. But a lot of background work on this. So how do we use this model? Okay, so the simplest one is what I call mode one. This is by analogy to Daniel Kahneman's system one, which is sort of a subconscious reaction. So you observe the world, let's call it X, run it through a perception system, also known as an encoder. It gives you a representation of the state of the world as 0. And from this, you directly compute an action to take. So this is completely subconscious. And there is a little neural net here, or maybe a big one, that just computes what action you should take, given the current task that the system is configured to solve. Okay, so that's mode 1. There is mode 2, and mode 2 is really the more interesting one. So that involves planning and reasoning. So in mode 2, and that's very similar to something in optimal control called model predictive control, which I'm sure a lot of people in the audience who deal with controlling aircrafts, for example, are very familiar with. So again, the state of the world, the observation from the world is this X variable, goes to an encoder that estimates the state of the world. It's of course, abstract representation. And then the system proposes a sequence of actions, and from the sequence of actions predicts the sequence of internal states, or the sequence of state representations of the world that will result from taking those actions. And those states are fed to the cost function. And what the purpose of the system now is to figure out a sequence of action here that minimizes the cost, the overall cost. Okay, so that's model predictive control. Through optimization, figure out a sequence of action that minimizes the cost, knowing a model of the world or the system you're trying to control. There's a lot of work on this in the context of robotics, sort of learning-based robotics by people at Berkeley, for example, and various other places. Let me skip this for now. The cost module would be constructed by having multiple cost modules, some of which are immutable, called intrinsic cost. So things that would protect the system from doing stupid things and hurting itself, for example. So those would be hardwired. And then a bunch of trainable cost, or critics, that basically are trained to predict the cost for any particular task that you want to set the system to solve. So the costs themselves can be trainable. And then the configuration of the overall cost function will determine the task that the system is meant to do. Now, one advantage to this whole architecture is that you could imagine doing hierarchical planning. So take the X, run it through an encoder, you get a sort of low-level representation of the state of the world. But then you could run this through a second encoder that will compute a more abstract, higher-level representation of the state of the world. And within that space, you might be able to do long-term prediction. So, for example, if I want to go from New York to Washington, D.C., I know that, so the cost function here would represent my distance to Washington, D.C., for example. I know that the first action I should take is probably go to the train station and catch a train. Okay, second action is catch a train to D.C. Now, to go to the train station, So this would represent my distance to the train station, to the Amtrak train station in New York. The first thing I need to do is get out of my building and catch a taxi to the train station. To get out of my building, I need to get out of my chair, go to the elevator, etc., all the way down to millisecond by millisecond muscle control. So this is hierarchical planning. And a big challenge, I think, for learning systems over the next few years is to figure out how to train a system end-to-end so that it discovers how to decompose complex tasks into a sequence of simpler ones, essentially. And dealing with the fact that the world is not deterministic, so you have to kind of deal with this as well. I'm not going to go into those details, but that's the idea. Hierarchical planning under uncertainty is, I think, the big challenge that we need to solve. This is what animals and humans are capable of doing, and that no AI system today really can do, as far as I know. At least no system capable of learning can do. Okay, so how are we going to build and train this world model? That's going to be a big challenge. And again, we're going to use self-supervised learning, as I explained earlier. Here is the main issue, though. If we're going to train a system to predict what's going to happen in the world, like, for example, by training it to predict what's going to happen in a video, the main issue there is that the world is not deterministic. So predicting what's going to happen in a video cannot essentially be done. There is an infinite number of plausible things that may happen in this video, and you're only going to see one in this particular instance. But the system will quickly realize that there are many plausible things, and you know, what kind of prediction can it make? So if you have a deterministic function like a neural net making a single prediction, and you train a system to minimize an error, the only thing that the system can do, if you have like multiple y for a given x, multiple future video for a given initial video segment, is basically predict the average of all the possible futures if this cost function, for example, is a least square. And that's not a good prediction, right? So you get blurry prediction. And in fact, this is exactly what happens. You see examples here at the top, video prediction, where a system has been trying to predict the frames in a video, and it makes those blurry prediction. Here, the second column of the panel at the bottom right are blurry predictions of a system trained to predict the position of cars from top-down video over a highway. And so this, you know, it's very difficult to do, right? And my answer to this is a new architecture, which I call JEPA, that stands for Joint Embedding Predictive Architecture. And this architecture does not predict Y. It predicts a representation of Y. Okay, so given an X, which is, let's say, initial segment of a video, and Y, which is a continuation of that video, both X and Y go into encoders, and the prediction takes place in this abstract representation space. So in this abstract representation space, the system is trained end-to-end to basically minimize the prediction error. And it's going to try to find a trade-off between extracting as much information as it can from X and Y in the form of SX and SY, but only extracting things that are easily predictable. So that all the really tough things that you cannot predict basically would be eliminated from the representations SX and SY. So this is to be contrasted with generative architectures. So the most popular set of architectures at the moment for things like self-supervised learning in NLP or in text are generative architectures, right? You give an X, you run it through an encoder and a predictor, and you predict Y, let's say the missing words or the next word in the text segment, and you minimize some prediction error. And what I'm recommending here is that because when you're trying to predict video, there's just too much information in that video that just cannot be predicted, let's eliminate that information by running Y through an encoder so that the SY now has a reduced amount of information. All the details, irrelevant details about the world are eliminated from it. And now we're going to do the prediction within that abstract space, SX and SY. So this is a joint embedding architecture, or joint embedding predictive architecture if you have a predictor here. There are several types of joint embedding architectures, simple ones that we used to call Siamese nets, where the two encoders are identical and their outputs are joint, and you're just trying to minimize the distance between the two representations for an X and a Y that are compatible. There's a lot of algorithms that are based on this idea. Again, it used to be called Siamese networks. There's a deterministic joint predictive architecture where this is just a deterministic function, and then a non-deterministic one in which the predictor, which is a deterministic function, accepts a latent variable z that can be varied over a set or sample from a distribution, and produces essentially a set of possible predictions or perhaps a distribution over predictions. So this is the full JEPA. This is the deterministic JEPA, and this is the joint embedding architecture without the prediction. But to understand those models, you might realize that although you can make the generative model probabilistic, there's no way to interpret joint embedding architecture as probabilistic models, because these do not compute a distribution of y given x, a conditional distribution of y given x, because to do this, you would have to invert this encoder, which may not be possible. So those are not going to be probabilistic models. And for this, I'm sort of suggesting to use a weaker form of handling uncertainty that are called energy-based models. And an energy-based model, essentially, you can think of it as a sort of an unnormalized probabilistic model, if you want, that essentially captures the dependency between variables x and y through an energy function, which is meant to give low energy to x and y's that are compatible and high energy to x and y's that are not compatible. Okay, so let's say x and y are scalar values, and your training samples are those black dots. You want to train your energy function here, f of xy, which will be some gigantic neural net, so that it gives low energy to the data points and higher energy to everything else outside the data points. Okay, so think of this as representing level curves, level sets. To do inference, you might be able to do things like that. So given an x, how do I find a y that is compatible with x? I just try to find a y that minimizes the energy while keeping x constant. To train those energy-based models, we're going to have to use one of two methods. There might be other methods that I don't know about, but pretty much all the methods I can think of fall into one of those two categories. And the main issue you have to deal with is the potential collapse of the energy function. So if you just ensure that the energy of the training samples, which are those blue dots, is low, you might end up with an energy function, an energy surface that is flat, and so therefore does not capture the dependency between the variables. So what you have to do is make sure that the energy outside of the manifold of zeta is higher. And there's two methods. One method consists in generating contrastive points, those flashing green points here, whose energy you're going to push up. And another set of method is that I call regularized method, are going to essentially minimize the volume of space that can take low energy, so that if you push down the energy of some regions of space, the other regions will have to go up in energy because there is only a limited supply of low energy volume, if you want. I prefer the second set of methods because the first set of method in high dimension will require a very large number of contrastive samples. So those are those two methods. Contrastive methods generate negative samples, or regularized methods make sure the volume of stuff that can take low energy is small. And so if you push down the energy of training samples, the rest is going to be higher more or less automatically. And I'm going to argue for the second set of methods. So I'm making sort of 4 recommendations here. Abandon generative models in favor of joint embedding architectures. Abandon probabilistic models in favor of energy-based models. Abandon contrastive methods in favor of those regularized methods, which I'll talk about in a minute. And also abandon reinforcement learning because, as I said earlier, it's very inefficient. So use reinforcement learning only when planning doesn't yield the predicted outcome, or to address the world model or the critic, which is the cost function. And a joke I make sometimes is that the purpose of reinforcement learning research should be to minimize the use of reinforcement learning because it's so inefficient. So this is not very popular within the machine learning community because those things are kind of pillars of machine learning, if you want, and telling people to abandon them. I don't expect you to read this, but this is essentially a list of known methods classified as to whether they are contrastive or regularized. And so things like masked autoencoders and LLMs, etc., are contrastive methods. And the ones I'm going to talk about now are non-contrastive. So first, excuse me.
Hey, Yann?
Go ahead.
Yes, we're running up against the end of the time we have. So
Yep.
give me another 5 minutes and then time for questions.
That's good.
Okay.
Thank
you.
So joint embedding architectures, you can train them using contrastive method, and it's been relatively successful going back to the early 90s, but more popular more recently. But the more interesting stuff is those regularized methods. So that's what I'm going to talk about. In particular, a set of techniques that I called for training JEPAs that I called VICRAG. So VICRAG, the basic idea of it is you maximize some measure of information content that comes out of the encoder, simultaneously with minimizing the prediction error and also regularizing the latent variable if you have one. The particular way to maximize the information content that comes out of the encoder is to make sure the variance of all the variables coming out is above a threshold, 1 in that case, and that the covariance matrix of the variables is as close to 0 as possible, so that, or essentially the identity as possible, so that the variable coming out of the encoder are uncorrelated with each other. And in fact, there is a trick to make them more independent, which I'm not going to go into for lack of time. Those things work really well for self-supervised learning. I don't want to bore you with details, but basically, if you pre-train such a system using this VICRAG technique, and then using a standard convolutional net architecture, you chop off the last layer, and then you fine-tune, you train the last layer for a supervised task like recognizing ImageNet images. It gets very good performance that are on par with all the other self-supervised learning methods that are known. A slight variation of this can be used to do segmentation, not just recognition. It's called VICRAG L for local. Works really well. But the last one I really want to talk about is something called image JEPA. So this is, or iJEPA, and this is a new technique. The paper was just put on archive less than a month ago, and this one only uses masking. So you take an image, you mask part of it, you run the full image and the partially masked image through an encoder. It's the same encoder, really. And then you have predictors on top of it that are trained to basically predict the representation obtained from the full image. But those representations are computed from the partial image. And just this type of pre-training allows to train a vision system that gives you excellent performance with relatively efficiently with a relatively modest amount of GPU training. So this is this idea, iJEPA, and I think this idea of using masking with the joint embedding architecture is going to take off over the next future. I'm not going to bore you with detail, but those things work really well. And what's interesting is that they give excellent results even on methods that do not use data augmentation. So basically, it's only masking, no data augmentation, and they work as well as the method that use sort of task-dependent data augmentation. Okay, so I talked about hierarchical planning already, so I'm coming to the conclusion. Essentially, steps toward autonomous AI systems we're going to use self-supervised learning in a big way to basically train a world model to predict the consequences of the actions of an agent. Uncertainty is going to be handled using this JEPA and energy-based model framework. A world model can be learned from observation with very little interaction, or at least as little interaction as possible. And then the system is capable of reasoning and planning by essentially, through optimization, figuring out a sequence of actions that minimize an objective that the agent has been configured to do. And we don't have a complete general recipe now for training hierarchical JEPA, although we're getting close with those image JEPA with masking I was telling you about. And a lot of the problems are going to be to design surrogate costs that drive the system to learn the stuff that we wanted to learn. And there's a bunch of crazy predictions, which I'm not going to go through unless you ask me questions about them. So thank you very much.
thunderous applause. I hear it. Okay. Let's start with a couple questions. There's one out there from Charlie Pfefferman. So this is where a Fields Medal winner asks the Turing Award winner the opening question. Charlie Pfefferman. We'll wait for Cindy to turn Charlie on with the mic.
Hello? Can you hear me?
Yes.
Okay, great. That wasn't the question. Okay, so I wonder whether one can characterize the sort of problems that might be solved by let's say any form of neural net based system. Are there fundamental characteristics of problems that make them potentially solvable by these ideas, and another class of problems that are just highly unlikely to be solved? Can we say anything?
Well, the short answer is no. The more complex answer is it's complicated. So the first thing is you can, from the mathematical point of view, if you take a two-layer neural net, so basically, a linear operation, a pointwise nonlinearity, and then another linear operation, you can approximate any function, any reasonable function, as close as you want with that by just having a very large number of, a very large dimension in the middle layer. So the mathematical answer to your question is yes, you can approximate anything you want. The practical answer is no, because for almost every function you want to be able to approximate, the size of this middle layer has to be insanely large. And so the solution to this is to stack multiple layers. Okay. And it's been a struggle for people like me for almost 2 decades to convince theoreticians that layers were necessary, because you can approximate anything you want with just 2 layers. So why would you need anything else? But in fact, in terms of efficiency, you do need multiple layers for the same reason that algorithms require multiple steps to compute something. You can always solve it with a lookup table, but
Sure.
So then what are can we characterize the type of architectures that will solve certain type of problems well? And that is completely unanswered, essentially.
So may I follow up, or is time too limited for that? Hello?
Charlie, go ahead.
Okay, thanks. So, all right, neural nets in principle can do anything for the reasons that you say. But in fact, neural nets can be trained. And while it takes very large computer resources by our present standards, the resources are negligible compared to what one might have thought without trying it. And I wonder whether there are characteristics of problems that are reflected in the feasibility of training. I didn't phrase my question precisely enough. That's actually what I meant.
Yeah, I mean, what is learnable in a reasonable amount of time, or with a reasonable amount of data, which is really the same question.
Yeah.
So not clear. So one theoretical objection towards a neural net early on was the fact that neural nets are trained by minimizing some objective function, and that objective function is almost always non-convex and is very highly non-convex. And so you can't prove anything, from convex optimization results or anything. You can't prove convergence or of anything. And so that was an objection. It turns out the fact that it's non-convex is not a big obstacle. Like, you can train those systems, and in fact, the bigger you make them, the easier it is to train them because it's easier to find a solution to an optimization problem if you embed that problem in a higher dimensional space, basically, right? You can get around mountains and stuff. So, and it's something, so, people like the intuition of it, had a hard time kind of landing in most people's mind. And then there is the other problem that was kind of thrown at neural nets by statisticians, saying, okay, you can make those neural nets really big, you can train them, but then they're going to overfit the training data, if you fit 10 points with a 10-degree polynomial, it will go through your points, but it will go kind of wild in between. But in fact, that seems to also not be a huge issue with what's called the double descent phenomenon, where things kind of spontaneously get regularized as you get sort of a bigger.
Let me finish hearing the conversation.
Thank you. Next, David McCannon. Cindy, I sent you a text for that.
No, hey, I'm here. Can you guys hear me?
Yep.
So Yann, I'm loving Dr. LeCun. We've known each other a little while, so I tend to call you Yann naturally. Emotions are necessary for autonomous intelligence. Absolutely agree. So going back to your idea of perception, I think of AI as perceptrons, right? How do we make them into perceptrons where their senses and sensory are making sense through our reality, right? Because obviously we can't detach ourselves from emotions. And then kind of looking at, I love the energy model. That's fantastic. So I'm wondering sort of like, where do you see this going next? Like higher dimensional space, absolutely. Problems will be solved in there in space in many ways. What do you see as the next step, say, for a group think, as they call it, a group think on how to link these together? From our perspective, computer vision has been a big research part of our side. And so, we're looking for the right teams to link what I would call monolithic metals, right? So monolithic metal structures that have things like photonic computing systems embedded in the monolithic metals that are intelligent and can guide us through space, my friend. What's next?
Yeah. So in the program that I talked about and the cognitive architecture is not instantiated yet, right? At least not in any way that is satisfactory. And there's a lot of completely kind of uncovered practical issues when trying to instantiate it. And so one big question is, can we train for example, we don't have a recipe today to train a predictive world model that learns how the world works by just watching video. And that would be something we need. And the techniques that we have at the moment are either too specific or not good enough or haven't been tried to the extent that they should. So there's a lot of unknown there. A few groups in the world are kind of working on this kind of stuff. I mean, certainly at FAIR, also at DeepMind.
Also, like I said, consciousness exists because we have only one world model engine. Well, also, we might argue that we each have our own kind of individual consciousness, right? Like you see the world a little different than I do, et cetera, right? So how do we, with spacecraft, I think we want to train our spacecraft. I look at our future spacecraft as living machines. They're not something we have to necessarily mess with all the time. They're a living intelligence that's made of metals and crystal technologies and able to dimensionally fold space.
Yeah, well, I mean, you want to provide them with the ability to learn and adapt, that are similar to animals and humans to some extent. And perhaps what I'm proposing might be a way to do this, but I can't give you a proof because we haven't built the whole thing yet. So a lot of unknowns there.
Right. Yeah. So in other words, like, can we say when we say language models? Can we say, let's take chemistry, and now chemistry becomes a language model with transform adapters in some way?
Yeah.
Or can we say physics? Now physics is a language model. So we're cross adapting instead of saying I'm speaking English, I'm speaking physics, I'm speaking geometry, I'm speaking chemistry. Are there ways do you think we can adapt these together?
So here is an example for you. The systems currently that are the best systems for predicting protein folding, for example, are transformers. They are exactly the same type of architectures that are used for natural language understanding. So you take a sequence of amino acids and you remove some of them, you train some giant transformer architecture to fill in the blanks, and then you use the internal representation as input to something that is going to predict the three-dimensional structure.
So whether we're speaking chemistry, physics, or English.
David, we have somebody else.
Yeah, I got it.
Okay, this is for Pat Langley, and then we got to realize we're at the end of our time limit here. Pat, are you connected? Cindy?
Yes, Dr. Langley, you can speak now. You're unmuted. it appears that his mic is not picking up, but at this point, we are right at the 3:30 mark. What I would like to provide for our attendees, because we had an amazing amount of questions that came through. I know that we did not even probably touch a surface of all the questions and answers for you. So I'm going to get this to Dr. LeCun for him to review and get that out to everybody, because there's some anonymous questions, but I think within the community, I think everybody would appreciate of seeing the answers and questions from everybody. So I will send that out post this session once we can get everything squared up. Does that sound good for our leaders that are on the call?
Yes.
Wonderful. Thank you. And again, we just want to thank Dr. LeCun for coming, and thank you. And again, thank you for the feedback in the chat. We will get you the Q&A, the questions as well as the answers going forward. And I would like to just turn for closing remarks to Dr. Roach.
Again, I want
Go ahead. Okay.
Doug, you go ahead and then I'll go, but let's just take about 30 seconds each. Go ahead.
For all of us, we want to thank Cindy for doing a great job. Done. Over.
Yeah, let me thank everyone who's in attendance today. Professor LeCun, always a pleasure and just a fantastic colloquium. We had over 400 attendees, folks. We busted our own limit. So Yann, thank you so much for helping us do that. And we look forward to our next colloquium. Over.
Well, thank you very much for having me, and thanks to everyone who attended for putting up with my speech.
This will be good. We need a bottle of Blanche Bage now. Yes.
Right.
Thank you, everyone.
So I think we're just the panel right now, right, Cindy?
All right.
We everybody's departing. I would need to close the session for all, or we can wait as people drop off if you wanted to hang on.
So some of the people asked questions in the chat and not in the Q&A.
I tried to steer them over to the Q&A, so
Okay.
a few of it.
All did.
I will be able to pull over all the reports. It
Right.
just helps it to be easier, but I will make sure that I pull both reports.
Okay, sounds good.
And Yann, Cindy and I were talking a little bit. We're going to try to capture the attendance, from what agencies and from which, either academia, industry, or government, try to get those statistics as well. But we had a very large crowd. I actually got kicked out at one point, so I wonder if bandwidth got a little tricky. But got back pretty, so no worries. Great talk.
Thank you, gentlemen.
Thank you.
Have a great day. I will
right.
end everybody. Thank you. Have a great day.
You too.
Cheers.
Okay. Bye.
Bye-bye.